To the sixth lecture. In this lecture, we will start the second method for the course. Okay, so the first method, which we call the basic, is what we call the basic probabilistic method, where we directly work with probability greater than 0 or probability less than 1 to make a deterministic conclusion. In this method, this method is known as the expectation method, and the main key idea is to make use of this very useful fact that expectation is a linear operator. What do I mean by that? If you have a random variable which is a sum, if you have a random variable which is, if you have a random variable which can be written as a sum of other random variables, then expectation of that sum is equal to sum of expectations, right? So expectation, this E and the sigma can be interchanged. Okay, this is known as the linearity of expectation, and we will make use of this to prove a lot of results. The first example is something which we have already seen. We showed that in any graph G, there is a cut whose size is at least half the number of edges. Okay, so E of G is the edge set of G, and this is a cardinality. And how did we show that? If you recall, we said we will the experiment that we set up was we will toss a coin at each vertex, okay, a fair coin at each vertex, and heads we will give it let's say color 1, tails we will give it color 2, and then we decide to keep only those edges which are between two differently colored vertices. Okay, so this gives a cut. Okay, because these are all edges that cross a partition, the partition of the vertices which contain color 1 to the partition of vertices, the part which contains color 2. And we calculated that the probability of each edge surviving, probability that an edge would survive, we calculated it to be 1/4. Okay, now instead of that, we could have done the same thing in a slightly different terminology, which we also discussed. I could have defined a random variable x to be the number of surviving edges, and xi to be a random variable which is either 0 or 1, okay, where 0 if ith edge survives and 0 otherwise, which means probability of xi equal to 1, probability that xi is equal to 1 is half, right? Because it's head tail and tail head, this will survive. Head head or tail tail, it will die out. Okay, this would also mean expectation of xi, which is equal to 1 into probability of 1, 1 into probability of 1 plus 0 into probability of 1, which will turn out to be half. Okay, so this is important. And then what could we conclude? Now we use this fact that your x, right, what is this number of surviving edges? This x is nothing but sigma xi I equal to 1 to m, if m is the number of edges. So you have one random variable xi for each edge. Since there are m edges, you have total of m different random variables, and this x is nothing but the sum of all those random variables, right? Why? Because this is just counting. Each edge that survives adds 1 to the count, each edge that dies adds 0 to the count, hence the summation. Now you use this formula for calculating expectation of x. This will be the sum of expectations of xi. Each xi has a expectation half, so this will turn out to be m/2. So the expected number of edges that survive is m/2, and hence if the expectation of a random variable is some k, then there exists at least one outcome in the sample space where the value of this random variable would be m/2 or more. Okay, how do we prove that? That's a easy proof by contradiction argument. If every outcome in the sample space had the value of this random variable strictly less than m/2, then the expectation, which is nothing but a weighted sum, in fact a convex combination of all of these things, that will also be less than 1. This was the argument. This we had already seen. I actually only intended to recall it, but I think I ended up doing almost all of it. Okay, so this is where we really use the linearity of expectation. So now let's see the second example. Okay, so first I'll state what is this example. It says that there is a tournament on n vertices with at least these many Hamiltonian paths. So I think I have to define two things here. Tournaments. So yeah, but tournaments we already saw in lecture 2, right? When we talked about this money lender making a gang of robbers, the object we used was tournament. So this is nothing but an oriented complete graph is what is known as a tournament. You take a complete graph on n vertices, and then you can give any orientation, but by an orientation we mean for each edge we should either orient it in one way or the other. You cannot, this is not permitted. Okay? This is not permitted. You can only orient an edge either like this or in the opposite direction. Okay, so this is what is a tournament. And now what is a Hamiltonian path? So in a graph, a Hamiltonian path is a simple path which passes through every vertex. Okay, so simple ensures that no vertex is covered more than once. That's the definition of a simple path. It's a path in which no vertex is repeated, and a Hamiltonian path therefore is a path in which each vertex is visited exactly once, right? So for example, if your graph is a complete graph on 4 vertices, what would be a Hamiltonian path? You can say start from, okay, this is a very bad color. Okay, you can start like this, then maybe go like this and go like this. Okay, this is one Hamiltonian path. What is another Hamiltonian path? Maybe you can do like this. Right, this is another Hamiltonian path. Each vertex has to be visited exactly once. Some of the edges may not be visited, but paths, as you know, has to really respect the edges. You cannot jump from one vertex to another unless those two vertices are connected by an edge. Now, in a directed graph, path in a directed graph like our tournament has the obvious additional restriction that the path should also respect the direction of the edges. Okay, so in this same example, but let me draw it in a slightly bigger fashion. Okay, so here let us say I orient the edges, something like this. So this is now a tournament. In fact, this is a T4. This is a tournament on 4 vertices. So what is a Hamiltonian path here? Yeah, so I adjusted the highlighter. So maybe this was one of the options which we had earlier, but now this is not possible because you see that I cannot respect this edge. Okay, so is there another option? Yeah. So this is still a Hamiltonian path because all the edges, we respected the orientation of all the edges. Okay, and is there anything else? No, this seems to be a sink in the graph, so anything has to really end here. That actually reduces the choices quite drastically, right? So I think in this graph, let's say I want to end here, then I can go back to either this vertex or this vertex. But if I go back here, okay, by the way, this is also a source. So this is a source, this is a sink, which means I have to really start from here and I have to end from here. So I had only this option or this option, but this option would have again got stuck because in the next step you would have to come here, which would have been the end of the path. So this is the only Hamiltonian path. So this is a graph in which you had only you had only one Hamiltonian path, right? Only one Hamiltonian path. Whereas how many did we have here? In fact, you can verify that any of the 4 factorial paths that you can think of are Hamiltonian. That's a property of a complete graph. In a complete graph, you just arrange the vertices in any of the n factorial possible order. Since all pairs are connected, that will be a right. Okay. I mean, and this is a useful thing to note. We will use that in the proof also, right? This n factorial here actually comes from there. Okay. Now, yeah. But now, can we construct a tournament in which there is no Hamiltonian path, right? Can we construct a tournament? You can pick your n, right? Such that there exists no Hamiltonian path, right? Try this out yourself as a exercise. Here we reached very close. We only had one Hamiltonian path here, but see if this is possible. Okay. So, but what is our, so this is an exercise, but what is our agenda? Our agenda is to construct a tournament with a very large number of Hamiltonian paths. Okay. We are going to construct, if you compare the numerator and the denominator here, the numerator is much larger. This is like 2 to the power n log n. Okay. And this is only 2 to the power n. So this is it's a very large quantity, and we are also trying to construct a tournament with at least these many Hamiltonian paths. Okay, so that's kind of in the other spirit as to this exercise question here. So what is going to be our approach? Okay, I again want you to pause and think, compare with what we did for the max cut problem. Can we do something similar? Okay, yeah, and the idea is, the answer is yes, we can do something similar. You take Kn and orient each edge independently and uniformly at random. Okay, this is your first step. Okay, so if you had taken a K4, you had 6 edges. So if you had taken a K4, you have 6 edges, which means you have 2 to the power 6 possible orientations. You can pick any of them equally likely, but that's a slightly complicated way of saying that. A better way of saying that is go to each edge. So you'll go to 6 edges one after the other, toss a coin. If it is head, you orient it in one way, tail, you orient it in the other way. So some of you, I mean, if you're very careful, you may be confused as to what does this one way and the other way mean. Okay, there is many ways to do that, but once you label, if you label the vertex set of K4 as 1, 2, 3, 4, then we will say that if the coin comes up head, then you will orient it in the ascending order, so that if this is I, you will orient it such that the j is greater than I. If it is head and if it is tail, then you will orient it so that the head, okay, the head is smaller than the tail. So this is one way to formalize what we mean by one way or the other, but that's not important. Okay. What is important here is now we have to set up this random variable x, right? X is a random variable, and we want to set it to be equal to the number of Hamiltonian paths in this tournament, right? So this orient, to get Tn. Okay, so I'm just introducing the notation Tn, and x is the number of Hamiltonian paths in Tn. We want to show, our aim is to show that this expectation is, our aim is to show that expectation of x is greater than this quantity that we want. Okay, so you already get a hint if you look at all these quantities here. So the next step is to write x as some x1 plus x2 plus some x, some m here. We'll think what is this m. Okay, so and each of this xi is going to indicate whether a particular path is a valid Hamiltonian path. Okay, so remember, if there was no orientation, then you had n factorial possibilities of arranging vertices in a particular order, because there are n vertices in total. So this number here is n factorial. Okay, so each of these random variable xi corresponds to one particular orientation, right? Now what is xi? Xi will be equal to 1 if that orientation is a directed, that's the main idea. In the undirected case, it's all is a directed Hamiltonian path and zero otherwise. Okay, so I mean, this kind of indexing may be slightly confused. If it is confusing to you, then you should actually think of this set, Sn to be the set of all permutations of the vertex set, which is n. So you know that the cardinality of Sn is n factorial, and then you should write this random variable x as some sigma element of Sn, x sigma, where each x sigma is equal to 1 if sigma results in a directed Hamiltonian path of Tn and 0 otherwise. Okay, both are the same. Here I made the subscript a bit more explicit because this 1 to n factorial is a proxy for each permutation. So here we, instead of using a proxy, we directly used the permutation as a subscript to index the random variables. Okay. Now what would be, so since we have already n factorial, guys, we are hoping that e of xi is 2 to the power n minus 1. And is that true? What is e of some x sigma for any sigma? Okay, so let's say in your sigma, your vertices are ordered as sigma 1, sigma 2, sigma 3, all the way up to sigma n minus 1, sigma n. When does this orientation become a directed path? It becomes a directed path if this edge is oriented like this. This is oriented from sigma 2 to sigma 3. This is oriented from this, and so on. Right? So what is the probability that this guy is oriented like this? Since it was a fair coin, it is half. Same thing here, same thing here, same thing here. And so what is the probability that this entire path is oriented consistently? How many edges are there? N vertices, which means n minus 1 edges, right? This is the probability that it is oriented correctly. So what is this? This is the probability that x sigma is equal to 1. That is equal to half to the power n minus 1. Remember, all the coin tosses were independent, and hence I can do this calculation, right? Now what is e of x sigma? So remember, this I will always keep on using. So let me even put that inside a box, right? So if x is an indicator random variable, what do you mean by if x is a 0, 1 valued random variable? This is what is an indicator random. It can take only two possible values, 0 or 1. Then expectation of x is nothing but probability that x is equal to 1. Okay, so since we are going to use this multiple times, I'm going to put this here. Okay, so that's what we are going to use, e of x sigma. Since here x sigma is also 0, 1 random variable, this calculation is what we had already done long back here. This is just this calculation, 1 into probability of 1 plus 0 into probability of 0. So 0 into whatever does not matter. 1 into probability of 1 will turn out to be probability of 1. Okay, so this is e of x sigma is equal to probability that x sigma equal to 1, which is 1 by 2 to the power n minus 1. Okay, so now we are done. Okay, so we have now we are ready to do our fourth step, which is to calculate e of x, which by linearity of expectation is e of x sigma, sigma element of Sn, and hence there are all these e of x sigmas are 1 by 2 to the power n minus 1, and you have n factorial many such summations. Okay, so this is exactly the number we hope to prove, and hence we can conclude that, what do we conclude? There exists a tournament Tn with these many Hamiltonian paths. In fact, it also tells you that there exists a tournament with at most these many Hamiltonian path. Okay, the theorem we were proving is at least, but the same expectation, expectation of a set of quantities cannot be smaller than the smallest quantity. It cannot be larger than the largest quantity. Okay, so both conclusions can be drawn from this point. Okay. Yeah, before going into the next problem, this particular problem also has a historical significance. Okay, this is from 1943 by Zelle, and this predates Erdős's lower bound for the Ramsey number, that, if I remember correctly, was 1949. So, and this is considered by many as the first use of the probabilistic method. Okay, so yeah, that's the historical importance of this problem. So now let us move on to our third example. So this is a problem regarding CNF SAT. Okay, in particular a variant of CNF SAT called E3 SAT, which we will describe slowly. But in the since there are some students from electrical also here, let me quickly define what is a CNF formula. A CNF formula phi is something of this form. It is some C1 and C2. Okay, so this is a notation for the AND operator, or in logic we call this the conjunction operator. Okay, so this conjunctive normal forms C part comes because it's a conjunction of clauses. Okay, so it is an AND of C1, C2, C3, etc. So phi is true only if all of C1 to Cm are true, because it's an AND of so phi is true if and only if all of C1 to Cm are true. Now, what is each clause? Each clause is an OR of literals. Okay, so maybe the electrical engineers would actually know this as a product of sum form. Okay, in Boolean circuits at least, this is known as a product of sum form, where your AND gates are at the top level and the OR gates are below it. So this is an OR operator, or the disjunction operator. Okay, and each clause is a OR of literals. And what is a literal? Literal is either a variable or its negation. It's either x or x bar, and each phi comes over a set of variables. Usually we refer to the number of variables as n and the number of clauses as m. Same way we refer to the number of nodes in a graph as n and number of edges as m. The number of variables in a clause, in a CNF formula, is referred to as n, and the number of clauses is referred to as m, conventional. Okay, now this is what a CNF formula is. The problem that we are going to study is whether a CNF formula is satisfiable or not. So when do we say that a CNF formula is satisfiable? Okay, we say that it is satisfiable if there exists some truth assignment. What is a truth assignment? A truth assignment is a function which sets each variable x1, x2, xn to either true or false. So maybe x1 is true, x2 is true, x3 is false, x4 is true, etc. But this can be modeled as a function from the set of variables to true and false. This is what a truth assignment means. But we say that phi is satisfiable if there is even one truth assignment, so that phi evaluates to true. Okay, that's the idea. But remember that I mainly want to highlight the fact that this is an existential statement. We only care even if one truth assignment satisfies phi is said to be satisfiable. The opposite, where you want every truth assignment to satisfy phi, then we say that phi is a tautology or phi is valid and so on. That's not what we are at. Okay, now what is a 3CNF? 3CNF is a special case of a CNF formula where every clause that you see here has at most 3 literals, which means it's an OR of either a single literal, or it's an OR of 2 literals, or it's an OR of 3 literals. So it can be something of the form some x3 or x4 bar, or it can be x3 or x4 bar or x5. Okay, so these kind of things are allowed, but you cannot have more than 3. That's what a 3 SAT has a restriction. Okay, and what is E3 set? With this E stands for exactly. So E3 set, we need every clause to have exactly 3 literal. So even this x3 or x4 bar was not allowed. Everything has to have exactly 3 literals. Okay. Now, why is this CNF formula so famous in computer science? First of all, it kind of models a lot of problems. Many problems can be, once you write this question express the question in formal logic, if you get a propositional formula which represents it, you can always convert that propositional formula to the CNF form, and checking whether a CNF is satisfiable or not is as general as checking whether a propositional formula in 0th order logic, okay, in propositional logic is satisfiable or not. Okay, and yeah, that is what the CNF set problem is. Okay, so this is an algorithmic problem. You are given a CNF formula phi, and you are asked to check if this decision problem asks to check whether this given formula is satisfiable. Okay, and this is the quintessential NP complete problem. Okay, first of all, it is a problem in NP in the sense that a non-deterministic Turing machine can easily find a solution, or equivalently a polynomial time algorithm can verify the solution. Now, this should be clear to everybody, even if you do not know Turing machines and the model. It should be clear that it is very easy. You can check in m plus n time whether a formula is satisfiable. What do? You run through each clause. When you are, sorry, I think I kind of said something wrong. What I mean is that given a truth assignment, it is easy to check whether that truth assignment satisfies it. So if somebody else says they have solved it and this phi is satisfiable, we can verify it easily in polynomial time by just going through each clause C1, C2, C3, etc. and checking if each clause evaluates to true, which can be done in n time. So total in some nm time, not n plus m time. You can easily verify whether a given truth assignment satisfies the given formula. That puts the problem in NP, but that is far from solving the problem in polynomial time, where the task is to find out this assignment, not to verify the solution which somebody else provided us, but to find out that. And we know that if this problem can be solved in using a polynomial time algorithm, then every problem in NP can be solved in polynomial time. So this was proved. This is the famous Cook-Levin theorem. This is the famous Cook-Levin theorem, and hence this is the special, sorry, I should have written it here. Okay, yeah, this is the quintessential NP complete problem. So if CNF set is solvable in poly time, then P is equal to NP. Every problem in NP has a polynomial time algorithm. So that's why this is very important. Okay, and even these restrictions E3 sat are still NP complete, which means even if somebody finds a polynomial time algorithm to solve E3 sat, then you still show that P is equal to NP, which is a very unlikely thing. It is still an open question as to whether P is equal to NP or not. So nobody believes that these algorithms have these problems have poly time algorithms. Okay, but what is the theorem that we will prove using our expectation method? We will show that maybe it is very difficult to check whether all the clauses can be simultaneously satisfied by a truth assignment. That is what is required for the formula to be satisfiable. But no matter which formula you give me, whichever phi you give me, this is the E3. This whole statement is only about this exact 3CNF. Whatever exact 3CNF formula phi that you give me, there exists a truth assignment which satisfies 7/8 fraction of the clauses. Okay, so if there are m clauses, at least 7m/8 clauses can be satisfied by this truth assignment. The claim is that such a truth assignment always exists. How do we? By the way, it's also known that, so this gives in some sense an approximation algorithm, and it is also known that this factor is hard. Okay, it's very difficult to have an approximation algorithm which will solve more than 7/8 of the clauses, or to check if something can solve more than 7/8 of the clauses. But that's a digression. We will stick to just proving this result. Okay, I want you to again pause, take a deep breath and see what would be the steps. Okay, what is the random experiment that you are going to construct? What is that total random variable x you are going to define? How are you going to decompose x into sum of smaller indicator random variables? What would be a good choice of the indicator random variables, and how you will calculate the expectation. Okay, so I'm assuming you have done that and you are only here to verify your answer, right? So what is the random experiment? The random experiment is a random pick an assignment T independently and uniformly at random. What does that mean? Actually, here I can just say uniformly at random because there is only one assignment here. So there are n variables, right? So n variables would mean 2 raised to n possible functions, right? 2 raised to n possible truth assignments. T's, you pick one of them uniformly at random. That's the same probability distribution can be also obtained by a more granular random experiment, which is you go to each variable, you have the variables x1, x2 to xn, right? You go to each variable, you toss a coin. If it is head, then you assign x, if it is head, then you say x1 is equal to true. Let's say x2 became tail, then you say x2 is equal to false, and so on, right? So heads true, tails false. So you can see that every possible truth assignment will occur with a probability 1 by 2 to the power n. There are 2 to the power n possible assignments, each of them have the same probability. This is your step 1. Now, what is your random variable that you want to analyze? So our claim is, what is our claim about? Our claim is about satisfying some number of clauses, right? So that is the parameter that we are aiming at. So this will be the number of clauses satisfied by T, by this random assignment that was being picked up. So now third, we should be able to write this x as some x1 plus x2 plus etc. Ideally, we would like x1, x2 to be indicator random variables, and each of them should be such that their probability of 1 is easy to calculate. So here it should be very natural because we are counting the number of clauses satisfied, right? Which means our random variables are this is almost natural. Okay, each random variable will correspond to one clause. Okay, and it will be 1 if that clause is satisfied, 0 if it is not. Okay, so xi is a random variable which is 1 if T satisfies the ith clause Ci. Okay, satisfies the ith clause in phi or Ci and 0 otherwise. Okay, so now you see that this summation is correct, right? Because every clause that is satisfied will contribute 1 to the sum. Every clause which is not satisfied will contribute 0 to the sum. So this sum is a clever way of counting the number of clauses that is satisfied by this assignment. Okay, now we have to calculate E of xi. Since xi is an indicator random variable, we already know that this is just equal to calculating the probability that x is equal to 1. But what is the probability that clause is satisfied? This is where we are going to use the fact that we are in this E3 set. So each clause Ci is of the form some xp, or let me just, some literal LP or LQ or LR. Okay, exactly 3 of them. And even if, since it's an OR, even if one of the literals evaluates to true, this clause is satisfied. The clause evaluates to true. So the only case when this clause fails to be true is when all of them turn out to be false, right? Now, when does LP turn out to be false? If LP is some x, then that is when x turns out to be false. Or if LP was some x bar, then LP is false when x is set to true. But that does not affect the probability calculation, right? So this whole clause is unsatisfied only when all 3 of them are false. Each of them has a probability half to be false because it was a fair coin toss, and since the coin tosses at these three have to be three different literals. Okay, actually I should have included that in the definition. Is CNF sat, where did I mention? Yeah, exactly three literals and corresponding to three distinct variables. Okay, that is important. Otherwise, in some sense, it's a cheating. For example, if I have x1 or let's say x2 bar, this is cheating because this is actually x1 or x1 is equivalent to x1. So this is a two literal clause kind of, written in a confusing way as a three literal clause. Similarly, if you had x1 or x1 bar, right, then this we know that either of this is surely true. So this clause is always satisfied, and hence I could have deleted this clause from my formula because this is a clause which will anyway be true. Okay, so this is not a serious issue that we say that the three literals should correspond to three distinct variables, and since they correspond to three distinct variables, this is independent. So the probability that this clause is not satisfied, which is xi is equal to 0, is 1 by 2 cube or 1 by 8, and hence this is 1 by 1 minus of that, which is equal to 7 by 8. Now you see where the 7 by 8 fraction comes from. Okay, so now you get E of x is equal to sigma E of xi, I equal to 1 to m. There are m terms, each of them is 7 by 8. This is what we were anyway hoping for. But remember, this xi, x1 and x2 are not necessarily independent random variables, right? If two clauses share a variable or a literal corresponding to the same variable, then their satisfying status is tied together, right? It's not independent anymore. But linearity of expectation does not need independence. Okay, that is why, in fact, that's the single most important reason why linearity of expectation is applicable in a wide variety of problem, precisely because you don't need independence. Okay, so yeah, so we have calculated E of x, and now rest is our general argument, right? Hence there exists a truth assignment from V to TF such that the number of clauses satisfied is at least 7 by 8 m. Okay, so if the average number of clauses that are true is 7 by 8 m, there exists at least one guy who is equal or better than the average. That is the idea. Okay, so next, maybe we'll do a couple of more examples in the next lecture, but we will wind up this lecture by summarizing what is this method. Okay, so most of you would have already figured this out, but I'm just repeating it here. The scenario that we are in is to show the existence of an object O. This was same in the basic method also. We needed to show the existence of some object O. But here, most of the time, we have an additional requirement. We have to show the existence of an object O such that a certain numerical parameter associated with the object is greater than or equal to some value or less than or equal to some value. Right? In the max cut case, we were trying to show the existence of a cut or a bipartite subgraph where the numeric parameter was the number of edges in that bipartite subgraph or the cut. We wanted to show that that was at least m by 2. In the tournament Hamiltonian path problem, we wanted to show the existence of a tournament with what is the parameter? The number of Hamiltonian paths in that tournament. We wanted that to be more than some n factorial by 2 to the power n minus 1. In the third problem, in the E3 sat, exactly 3 sat, we wanted to show the existence of a truth assignment. And what is the property? The numeric parameter that we were calculating was the number of clauses which will be satisfied under this truth assignment. We wanted to show that that was 7 by 8 m. Okay, so and most of the time the object that we are going to construct is the one we are going to construct using our random experiment. Okay, so the first step is to design a random experiment. Okay, and this design is to be highlighted because that's where our thought should go in. A random experiment whose sample space contains the objects that we are interested in. The second set is almost natural. Your x we will define to be this. What is this x? This is x, this is the same x that we have here. Okay, that is this x. This is nothing but the parameter function. Okay, now does it fit the definition of a random variable? Recall that a random variable is a function from the sample space to the real numbers, right? So here the sample space consists of objects, combinatorial objects like graphs or truth assignments or tournaments that we create, and this is a numeric valued function, which is another way of saying that it's a real valued function which you give any of these combinatorial object as input, it will return a number. So this qualifies to be a random variable, right? So that is why the definition of the random variable does not need any thought. It is automatically the parameter on which we want to give a guarantee. That is our random variable. Okay, we are in a discrete setting, so we don't have to bother about whether this function is measurable or no such issues are there. In fact, most of the time in combinatorial settings, this numeric parameter would be a counting random variable. What is a counting random variable? A random variable whose range is a subset of natural numbers. But that's also not important. Next is we decompose. Okay, this is again a critical step. Okay, we decompose x as a sum of simpler to compute random variables, and most of the time we will decompose them as a sum of indicator random variables. What are indicator random variables? It is a 0-1 valued random variable. They are also known as Bernoulli random variables. Why do we call them indicator random variables? If the random variable is set to 1 to indicate that something has happened, and 0 to indicate that something does not have happened. That's why we call them indicator random variables, and this is a tricky part. Okay, we try to decompose them as a sum of this, right? And then we calculate the expectation of each of these smaller random variables. Now, if this turns out to be difficult, we will go back to step 1 and try to see if our experiment can be tweaked, can be redesigned so that this split up and this expectation calculations are easy. Now, we did not have to do any parameter tuning here because most of the time the claim itself, what we set out to prove, already had the value of k. We were not asked to guess what is the value of k. Maybe in the next lecture we will see that. So here there was no tuning involved. We just showed that this expectation of this random variable, which is easily calculated as a sum of the expectations we calculated in step 4. So step 5 is no-brainer. Okay, you can just add up all the expectations you calculated, but you have to show that this is greater than or equal to k. Then this is the general philosophy of the expectation method. If you can show that e of x is greater than or equal to k, then there exists at least one object in particular in the sample space of your random experiment. But we don't want to say that the final statement that we are going to claim is irrespective of this random experiment. So we will just conclude that there exists an object O in which this numeric parameter that we are studying is at least k. Okay, so this is the summary of this method. Okay, maybe I'll just rotate my screen so that everything comes in one screen which you can screenshot. Okay, so this is the expectation method, or some people call it the first moment method. Okay, we'll see a few more examples in the next lecture. Thank you.